Welcome to this session. In this session, we will look at the assumption of a logistic regression model. Because if we want to infer valid claims from a logistic regression model and its coefficients, then some assumptions have to be met. I will briefly showcase this in a contrast between the assumption of linear regression and logistic regression. So, in linear regression, we have something called heteroscedasticity. That is the case when we have a different variation across the predictor, the independent variable. Let's see. Here on the x-axis, I plot the experience or the professional experience in years, and on the y-axis, the salary. Then we ask people about their income and professional experience, and we may see something like this. So this is our regression model, and we see that people with low experience tend to earn the same salary. So here in this area of low professional experience, all subjects seem to earn more or less the same. Whereas in higher years of experience, there is much more variation in salary. What we would expect is that there is the same variation across the range of experience. So this is a violation about heteroscedasticity. Well, then there is again normality of errors. When we have something like this is our data, x and y, and we draw a regression line, then we look at the error. That's the difference between the data point and the regression line. And when we plot the magnitude of the errors, that's this distance of all our data points, we expect something that looks like a normal distribution. So the good news is that in logistic regression, this assumption do not hold true, because the logistic regression assumes that the error terms are binomial, and they follow a binomial distribution by the design, by the data structure. So because we have 0 and 1 variable as the y variable, either a patient has the disease, that's a 0, or he or she doesn't, and that's a 1. So if we have this as the dependent variable, we can just check this and say that's fine. We have the first regression assumption met. Then there is something called the independent of y values. So we also say that there should not be autocorrelation in linear regression. Well, that is when the first data point influences what we measure on the second. So for example, on a chart where the price of shares is displayed, then we see something like this. You should recognize this from the stock market. You see that there is some kind of trend in the data. And you see that when we know that there is an upward trend, then we expect the next value be a higher value than the value before, because we can say this with a certain confidence because there is some kind of trend in the data. For medical or clinical research, it would something like this. We have a patient and we ask him for the presence or absence of disease. And when we investigate the next patient, then the first patient should not influence the status of the second. So we have to check this even in logistic regression, and we have to check this by the study design and how the data is collected. Does the data collection influence something called autocorrelation? So you should check this. And there's something called linear relationship between the independent variables and the dependent variables. So you expect something like this and not something like this. Yeah, it's hard to fit a line through this data with a linear regression model. This holds actually true for the logistic regression. Here we expect a linear relationship between x and the logit. We assume this actually in a logistic regression model. So you see that a logistic regression model, we should just check the independence of y values, and this is even given in most cases. One brief addition, of course you should check for multicollinearity. This is true when the independent variables are correlated with each other. So you should check for multicollinearity. But in general, you see that in logistic regression, most of the assumptions are already met if you have a binary y variable.